Mark your own, here we go. Oh, we have good old Anne. Given the following pair of parallel plates. So parallel plates, in terms of my formula sheet, I'm not using equations that have an R in them because R stands for radius, which is round circular point charges. If it doesn't have an R in it, that means I might still be able to use it. If it has a D in it, I'm going to use it. It wants the magnitude and direction of the electric field. I'm going to give you 1 mark for the magnitude, 1 mark for the direction. Our symbol for electric field is E, not F. F is for force. E is for electric field. And I can't calculate it by going K, Q over R squared. That would be the electric field for a point charge. I can't calculate it by going the force at a location divided by the charge at that location. It would work here if they told me how big a charge was between the plate and if they told me how big a force it was experiencing. And in fact, I may use that for part B or part C later on. I don't know. I'm going to use the change in voltage divided by the distance. Now, on the test, if I gave this as a multiple choice question, and you'll also notice in your review, often they give you this distance as well because they just want to see if they can trick you into using the length of the plate instead of how far apart the plates are. And it's how far apart the plates are that makes a difference. We're going to pause for a second. So the change in voltage, I have to be careful. It's not 500. We're starting at negative 250. So I think the change in voltage that we're traveling through is 750. The distance is 0.055. And so in between the plates here, there's electric field magnitude of 750 divided by 0.055. 13,600. And you can say volts per meter, or you could say newtons per coulomb. That gets you 1 mark. Now I need the direction. I imagine a little positive charge right there, and I ask, which way would that positive charge want to move if it could? Which way? Down. Direction A, south. I'm going to say down. 1 mark. Suppose an electron is placed at location A, right at the bottom of the diagram. What will its final speed be when it hits location B at the top of the diagram? Ibrahim, what does this question want me to find? Velocity? Say no. What does it want me to find? No, B. Starts with the letter S. Did it say velocity or did it say speed? I do pick my words carefully. That probably means I should use a scalar approach. I'm going to think about maybe energy and conservation of energy. You know what? Mathematically, an electron going from here to here is the same as picking an object up, giving it potential energy due to gravity, and dropping it and letting it hit the ground. All of the potential energy is going to turn into kinetic energy. So I'm going to solve this using conservation of energy. I'm going to start out by going KE initial plus PE initial equals KE final plus PE final. Now, if I wanted to, Sean, as a shortcut, I could go, you know what, it's starting at rest and it's hitting the ground. Really what we're saying is all of the initial potential energy is going to turn into kinetic energy. And you might see me do that sometimes in one of my solution keys on the ultimate review. I don't know. I may have just done that step in my head and said, look, this is like lifting an object up, giving it potential energy and turning it into kinetic. Now I'll bring those back just so that the whole equation is there, because some of you like to see the meticulousness, and we'll just cross it out. Now kinetic energy hasn't changed. It's still a half mv squared. Potential energy, not mgh. This is not gravitational potential energy. This is qv. That's sort of on your formula sheet, David. It's in the definition of voltage, where I defined voltage as the amount of energy per charge. You can rewrite that to get potential energy by itself. They want the speed. So Ibrahim, I think I'm going to times by 2, divide by m square root. I think the speed is going to be times by 2, divide by m square root. What if I wanted to, oh, I like this question, I like this question, I like this question, except it's a little easy. What if I wanted to make it a little more difficult? I might give you an initial speed so that KE initial wasn't 0. Or I could tell you how fast we hit the wall and ask you how many volts did we travel through? What was the voltage of the plate? Okay, that, or if I really wanted to be mean, I could give you the final speed, ask you to find the change in voltage, but actually tell you that this one was negative 250 and say, what was this voltage? And you need to realize, well, I got a change in voltage of 750 volts. This isn't 750. This has got to be 500 so that I get my 750. That would be really, really mean as well. Hint, hint. Meanwhile, here, 2. It's an electron, and we said here we put the positive charge in because it's inside the square root, and we know we're going to be taking the square root of a positive number. The change in voltage is 750 divided by m. It's an electron, 9.11 times 10 to the negative 31. Hit pause for a second. Crunch the numbers really, really quickly. 2 times it's an electron times 750 divided by it's an electron. Square root of that. Do you get 1.62 times 10 to the 7th? People nodding? V equals 1.62 times 10 to the 7th. Before you turn the page, first of all, if you got that 4 out of 4, otherwise I would probably go something like 1 mark, 1 mark, 1 mark, 1 mark. There's another way you could have done this. You could have done this using physics 11 acceleration. You could have said, I know VI is 0. You could find the acceleration. It's going to be the force divided by the mass. You know the mass of an electron. What's the force going to be? Well, that's going to be Q times the electric field. What's the electric field? You could use your answer from A, or if you wanted to do it algebraically, you would say it's voltage over distance. This would have given you the acceleration. You could have used the distance of 0.055, and then you could have solved this using VF squared equals VI squared plus 2AD. You'll notice to get the VF by itself, I still have to square root. You'll notice there's a 2 in the top. If you did this algebraically, you would find you ended up with that same expression popping out inside the square root, and you would get the same answer. And the reason we can use forces is because in between plates, the electric field is constant, therefore the force is constant, and so we can use a few more of our physics 11 tricks, which is kind of nice. Now you can turn the page. Oh, yeah, you know what? Here's a good example of what I was saying to you earlier. Now, here, I'm asking you to find the final speed. I would also have no problem giving you the final speed and asking you to find the initial speed. I would have no problem giving you both speeds and asking you to find how many volts. I would have no problem making this voltage negative so that the electron starts to slow down and asking you how fast it leaves slower or whether it stops or not, where the final speed would be 0 and having you figure out how many volts it traveled through. Okay? Pause one more time for a latecomer. So again, Ibrahim, I said, what's the final speed, not velocity? Although I think you could solve this using forces and acceleration. I'm going to solve this using conservation of energy. Kinetic initial, potential initial equals kinetic final plus potential final. Here, the only one that's 0 is that one. Once it reaches this spot here, it's used up all its potential energy, and now Newton's first is going to kick in. It's going to keep going in a straight line at a steady speed. A half m v initial squared plus q v equals a half m v final squared. I'm going to choose to go times by 2, times by 2, times by 2, because that gets rid of a couple of 1/2. It makes the equation a little bit nicer. I get m and vi squared plus 2qv equals mv final squared. And so now I can just divide by m square root, and that'll get me there. What am I shooting? It's an electron. 1.6, no, the mass, Mr. Dueck. 9.11 times 10 to the negative 31. V initial, 2.1 times 10 to the 5th squared. Plus 2, it's an electron. Voltage is 150. It will speed up because it's going to be attracted to the positive side. All over 9.11 times 10 to the negative 31. I think I can do this in one step in my calculator. Bracket 9.11 times, no, not times, Mr. Dueck. Use your scientific notation button. Negative 31 times 2.1, scientific notation button, 5th squared, plus 2 times 1.6, scientific notation button, negative 19, times 150, close off the top, divided by 9.11, scientific notation button, negative 31, square root. Did y'all get 7.26 times 10 to the 6th? People nodding? Meters per second. If you got that, 7 out of 7. Otherwise, I would probably go something like 1 mark for that, 1 mark for that, 1 mark for that, 1 mark for the numbers. What have I just used up? 4, 5. I need to get 2 marks out of here. I'd probably give you 1 mark if you cross that out. And, oh, I don't know, 1 mark for the square root, or I'd do something or other. Key idea, this line here. So as far as I'm concerned, the variables here are V initial, V final, V voltage, or the charge. I would have no problem giving you any 3 of those and saying, find the 4th one. Okay? I would have no problem giving you a situation where the electron is slowing down by making this negative and asking you to figure out how many volts I needed to bring it to a stop, for example. That would be a nice little question as well. I don't think I'll ask you to find M. If I don't think I will, but for what it's worth, how many M's are there? 2. How many would I prefer? 1. I'd get them to the same side. Oh, and then I'd use the grade 9. I'd factor the M out and get whatever I needed to by itself. Although I'm trying to think if I've ever done that. Later on, I'll ask you to find a mass, but that's when we're using cyclotrons. Right now, no. Okay? That's the quiz. If you'd be so kind as to put a score on there out of 13, please.